Hello and welcome to the Club One YouTube channel. My name is Ray, and in this video I had planned to actually configure Fred's left hand on Fred, but I've got a bug there I've got to work through, so I'm going to look at the I2C bus. Now recently we've done some modification to the PCA 9685 service. This is the one that drives the 16 channel I2C, the I2C 16 channel servo driver. It's had some of the improvements include the sleep function now works properly, and we're going to have a look at the I2C bus a little bit closer to see how all that works. So to make that work, I've actually got sitting on the bottom, the bottom left side, I've got the logic analyzer to capture the waveforms. On my camera here. Okay, so now I've got my camera working again, I have my logic analyzer here. I will try and put a link in the video to this. Over here is a Raspberry Pi 3, and it's the one currently running Fred Online, so you'll actually see some of that in the background here. There we go. So I've got the brains of Fred. That's where the brain search runs off to Wikipedia, and the bot that connects it to Discord. Now over here is a PCA 9685, also known as an Adafruit 16 channel servo driver. It's connected to the Raspberry Pi using this wire for the I2C bus. Now if you're familiar with these boards, here's another one over here, not connected. They have terminals on each end so you can daisy chain them. So I've connected the logic analyzer to ground. I've connected the purple wire to the serial clock on the I2C bus. The blue wire is the serial data on the I2C bus. And then the green wire is connected to channel 0. I've got this servo physically connected to channel 1. And channels 2 and 3 are connected to 2 and 3 on the outputs. So to make all of this work, what we're going to do is first go to runtime. We'll create a service called Raspberry Pi. We do need the Raspberry Pi service to work. You start typing in this area here, it will come up, and it's been hidden away by my two boxes. Just shrink this down a little bit. Okay, so now you can see here I've entered in Raspberry Pi and Raspberry Pi, and then we just hit Start Service, and that gives us a Raspberry Pi. I'm just going to move this. Okay, so if we hit scan the I2C, we should see we've got one device here at address 40, and that's this device here. And you can also see I've had a response come up on the logic analyzer. So this band here, and I can zoom in on that if I can find it. Okay, so if I zoom in on that, you can see lots of little messages coming through. I can make that wider. And so what we get is the data line is being held high to start a signal being transmitted across the I2C bus. The data line gets pulled low. Both the clock and the data line are high to start with. After it comes low, the clock line then comes down. There is a period of 15 microseconds. Sorry, that's the period. The width here is 10 microseconds. And then we go into our regular clock pulses of 4.9, so 10 microseconds period. Data is then transmitted along after our start signal, and in this case it's a signal to write to address 1, and what we see here is no acknowledgement. So the way the I2C bus works is it's held high by resistors on the bus. Each device on the bus has the ability to pull the data line down to ground to signal a data state. The clock signal is only controlled by the bus master, in this case the Raspberry Pi. So initially the Raspberry Pi will pull the bus down on the data line and then start the clock after a given period. Once that clock's running, it can then transmit its data, and then it will release the serial data bus, which will allow it to go back up high. If there is a device on the bus responding to that address, then it will actually pull down and hold the data line down, and that's considered to be an acknowledgement. So when the Raspberry Pi, MyRobotLab, does a I2C bus scan, which I've just done, it's actually just looking for an acknowledgement from the address, and it will actually send a read and a write to each individual address, all 124 or 126 addresses, looking for a response. Whenever a device responds, it just holds that acknowledge line down for that clock cycle. Alright, so let's get back to our web page. So what we're going to do is go into runtime. We've created our Raspberry Pi. The next thing we need is our service for the PCA 9685, which on MyRobotLab is called the Adafruit 16C servo driver. We're just going to call it PCA1 and start. So it appears over here pretty quickly, even on a Raspberry Pi 3. Now this is on these Adafruit boards. We have up in this corner, or this edge here, a heap of solder pads. I might actually bring that up higher if I can. Where do I put that on? So over here are a heap of solder pads, and if you short these solder pads across, it will change the address of the device. So you've got A0, A1, A2, A3, A4 and A5. If you short this pad here, the A0, add 1 to the address. If you short this pad, add 2. So in this particular board, this one is shorted, so this one would be an address 42 hex. If you short both this one and this one, you add 1 and 2 to the address, and so on, each pad being a double of the previous pad. In this case, none of the pads here are shorted, so it's at the base address of 40 hex. So we've got 40 hex there. The I2C bus on the Raspberry Pi is on bus 1. That's the one that's brought out to here that we're using. Let me switch back to our screen. And the next thing we need to do is select an I2C controller. In this case, the Raspberry Pi is the only one available, which is why we had to make the Raspberry Pi service in the first place. Now we can attach that. And if I set up my logic analyzer, we probably would have seen that attach go through. That was the detach sampling. And if I set it up attach, and select Raspberry Pi, select bus 1, select address 40 and attach. Still waiting for trigger, but it's attached. Alright, so the next thing we want to do is create a servo service. We're just going to call this test 1. Start the service. Test 1. Go to control, find the pin. This is attached to pin 1. And the PCA 1. Attach. Basic, and you can see the signaling came through over here. So with this one, you'll see a write to address 40. Hoping you can read that. So let me zoom in on that one. So you can see set up write to address 40. We got an acknowledgement. It then sends to register 0 and 10. That configured the device. That makes sense. So the 0 and 10, the PCA hadn't been used at that point, so Raspberry Pi service, or the PCA service, actually configured the hardware device, PCA 9685, and configured it to reset and start up. After it completed the reset and start up, it then selected the register FE and then proceeded to write some data to it, which is the clock frequency. After it did that, it then told it to start running. So it put the clock into hold to start with back here, set the frequency of the clock, and then start the clock back up, enabling the incremental register adjustment. And that turns out to be pretty important. The next thing we do is we set our register to 0A. We set the 16-bit value. We're only using 12 bits out of that 16-bit value. So we set the start time to be 0. This is the way the PCA 9685 works, is it has a 12-bit counter that's continually cycling. When it starts at 0 and goes up to 4095. When it would count up to 4096, it actually cycles back to 0 and then just keeps counting again. The outputs are a PWM control, and the original design for the chip that we're using was for LED lighting. And to stop all of the LEDs coming on at exactly the same time and hammering the power supply, it was designed so you could actually turn on the LED at different times and then turn them off at different times to help spread the load across on the power supply. The way we do this is we set an on time first, so whenever it reaches that time in the clock, it turns it on. And then the next 2 bytes is 16-bit value, again 0 to 4095, and this is where it turns it off. So we're now writing an off time. So we've turned it on at 0 and we're turning it off again at this time in hexadecimal. And that produces a pulse. As we move our servo, we send more pulses. So if we look at this one, all it's doing is writing to the same address, but the turn off time is slightly different. So I'm going to actually demonstrate this as a feedback on this wire here. To do that, we'll create another service. So back to that. Runtime, call it S2. Make it a servo. Start service. Test 2. Control, select pin 0 in this case, PCA, and attach. And here we have our output start. So if we zoom in on this first one, you'll see we've got a write. To 06, which is the very first output channel, because we selected output 0. And then we've got our start timing, and then we've got our stop timing. So 79 and 01. And shortly after that, we start seeing our PWM signal. Now, if we measure the timing in there, that is 1.4239 milliseconds wide. And that's pretty close to center for a standard servo. All right, so that's the easy part. As we want to change its position, we send more pulses or more commands, and that just changes the pulse width. All right, so that one's pretty straightforward. That's waiting for my next I2C signal to go through. So with the next one, what I want to do is show this set pin. I'm going to use pin 2, and I'm going to set it to 0.5. So we're actually doing this through a Python script because there's no other way to do it through the user interface yet. And we can actually send a percentage, so a value between 0 and 1. And if I execute that, we can see our PCA is our logic analyzer is sampling, and we've now got this signal appear down on PWM2. I zoom in. So we've got our setup to the device. So select the address. We're looking at register E hex. The turn on time is again 0, 0, and turn off time is 8. So that must be least significant, most significant byte. Shortly after that, we see our PWM signal starting. And our PWM signal has a period of 15.48 milliseconds. with a duty cycle of 50%. The frequency is 64.622, which is the same frequency as we've got for our servo output. So this is one of the limitations that we've got with the PCA 9685. You have got one clock which drives the whole board. And so we can adjust that frequency. It's not that difficult to do, but keep in mind that it does affect the performance of the servo output. The higher the frequency you can run, the higher the resolution you get on your output in the range, because the control for the PCA 968 or for the servos is in milliseconds, and if we change our frequency for the board, then our counts will change for each servo. So the lower the frequency you run, the less counts we have available to play with on the servo. There is an upper limit though. If you go too fast, then your servos won't keep up with the signaling and they will fail. So the better quality digital servos are good up to around about 70 Hertz for the frequency update. But in this case, you can see here we've got our 50% duty cycle. If I change this value in here to 80% and execute that. Actually, if I was smart, I would reset that first. And there you can see here our duty cycle is 79.98. It is possible to change the frequency that we are running at, and to do that you set PWM freak. So I'll actually do that. PCA 1, set PWM freak. Now this is where it's got a little bit of an error. It does want you to set the pin number that you're going to use, which doesn't really matter because it's only one for the whole of the unit, and then the frequency you want to run at. So in theory 60, but we can run slower, 50. Execute that. Let me just .63, it's not exact. In fact, it's not even close. That's something I'll look into in the near future. I'm not sure if these boards are accurately clocked internally. It is working off the internal clock. But I know this servo works at 60 Hertz, so let's put it back at that. Because you might have noticed that servo moved when I ran that. Now, one flaw I have got still to try and work out is when I set this to 0. Let's capture that first. I am capturing a lot of data now, so I could capture the idle shutdowns. So you can see here that this output is now at 0. If I set it to 1, try that again. You can see here that we're pretty close to fully on, but it's still spiking down, and that's just for one count. I will try and find that bug and fix that at some stage, but it's a lot closer than it was. In our test 1 with our servo, it's still energized. If I go back to control and set auto disable, and that rest we're capturing. So you can see here we're writing to servo 1, set the speeds. We scroll right out, we'll see there's a stop at some point. Oh, I sent this one. I sent for one I'm not monitoring. That's intelligent of me. Let's try that again. This time we'll do it on this one. Control, set for auto disable. Sampling at the moment. And you can see there it shut down. Alright, well that'll do for this video. If you like these videos, don't forget to click on like, subscribe, ring that notification bell. It's a form of support that helps the channel a great deal and costs you absolutely nothing. If you'd like to support the channel further, I do have a Patreon account and there will be a link in the description. I'd like to thank my long-term Patreons, VIPs Go Lucky and Lorenz Berger, and my builder Patreon, Elmorales45. As mentioned before, this Raspberry Pi is running a chatbot for Fred on Discord, and you can have a chat with him by going to the Discord server. There is a link in the description, and we'll see you in the next video.